Hello and welcome to our overview of Senior Design Project 144, the electric conversion of a gasoline-powered lawnmower, sponsored by Dr. Gibbs. This project will be performed by Bardia, Mower, David Dodson, and Jimmy Truong. A lawnmower will be provided by the sponsor. The gasoline engine will be removed from the chassis and replaced with an electric motor. To drive this electric motor, our team must design an onboard electronics battery system and subsequent subsystems. The design requirements have been defined to include three major subsystems. These subsystems are a motor controller, a rechargeable battery pack, and a battery management system. The battery management system will consist of a battery monitoring system to ensure that the individual cells in the battery pack are not damaged during operation, and a battery charging system to recharge the battery pack after use. Next, these three main subsystems will be combined through total system integration, creating a prototype. This prototype will be tested to make sure that it meets the following system requirements that are defined for this design project. These design requirements range from the design of a user interface, which consists of an LED battery charge status indicator and a motor speed throttle controller, to the implementation of user safety features and system protection measures. To address these requirements, a bail switch will be used on the handle of the mower for the user safety, and all of the system circuitry will be in an enclosure to protect it from water and debris. System constraints must also be considered in this design. The system is constrained to the physical dimensions of the provided chassis and must operate in an RPM range around 3000 RPM, just like a gasoline-powered lawnmower. The blade length will also be fixed at 21 inches and must rotate in a clockwise direction to properly cut the grass with the cutting edge of the blade.
Additional assumptions have been made in order to create an electric lawnmower to replace traditional gas mowers while matching its performance. The mower is expected to run for 1 hour beginning with full charge. It has a motor output between 500 to 1000 watts. Also a removable and rechargeable battery pack. The battery pack will be removed from the chassis to be charged. Power connectors will have reverse polarity protection. Data connectors and power connectors will be incompatible to avoid damaging the system. The lawnmower should be light enough so it can be used by someone with average strength. Reasonable environmental protection to spraying water and dust. Motor should also operate at an optimal blade speed. The system begins with the power source, a 36-volt battery pack followed by a master switch to fully disconnect the battery pack from the system. When it is connected, a DC to DC converter converts 36 volts to 3.3 volts to power the battery management system, or BMS. BMS is responsible for monitoring each battery cell voltage in operation and during the charging state. It also powers the motor controller when the battery has sufficient charge. There is an user interface to turn on the controller, control the blade speed, and read the battery status. System control unit generates PWM signals and transmits them to the motor driver to be amplified and drive the motor. The motor is equipped with Hall effect sensors to provide feedback to the controller in order to maintain speed with respect to the reference input. Three different types of electric motor have been evaluated and studied as possible candidates to be used in this project. The first option is a brushed DC motor. It is very simple to integrate and operate due to requiring a single DC input signal and a single channel amplifier. Motor speed can be controlled using PWM signal. On the downside, it has a low average service life of 1,000 hours. It is because of its brushes making physical contact with the rotor. Brushless DC motors yield an average efficiency of 75 to 80%. The second option is a brushless DC motor, which has a more complex structure and operation method. Operation of this type of motors require a motor driver capable of generating three-phase modulated DC power signals. Motor speed can be controlled by varying the frequency of modulation. It has a longer service life averaging about 10,000 hours. No maintenance is required for these type of motors. Brushless DC motors yield an average efficiency of 85 to 90%. Our last option for an electric motor is an AC induction motor. These type of motors have a simple yet novel working principle shown in this picture. AC induction motors operate by taking alternating current as input, where the motor speed is controlled by variable frequency drive controller. On the downside, in order to use these type of motors, direct current needs to be converted to alternating current, hence yielding a lower power efficiency. AC induction motors yield an average efficiency of 80 to 85% and have a service life greater than 10,000 hours.
This table will show the number of cells required to generate various voltages for the battery pack. We are interested in 36 volts, therefore lithium polymer and lithium ion needs 10 cells to generate 36 nominal voltage and 42 charging voltage. Lithium iron phosphate requires 12 cells, which will generate 39 nominal voltage and 43.2 charging voltage. For our design, we will use lithium iron phosphate. The reason being is that it has a higher power density and can maintain charge more efficiently when compared to the other battery compositions. The consequence is that it has a 3.2 nominal voltage per cell, and it will require a battery management system to monitor the cell voltage and current. There are many reasons why we have chosen lithium iron phosphate. This table shows the battery characteristics of 4 different battery compositions. If you look at lithium iron phosphate, you can see the advantages over the other types. For example, lithium iron phosphate has 220 for energy density, 2,000 to 7,500 for cycle life, and costs less than 14 cents to purchase. Because of these advantages, we have decided to use lithium iron phosphate. Our design will take 7 months to complete. I, Jimmy Truong, will work on the battery pack design. David will work on the brushless DC motor design, and Bardia will work on the microcontrollers. These tasks should be completed in 5 months by the end of October. After that, we expect it to take roughly 1 month to perform system integration. The remaining time will be used for the design revision and the presentation. For our learning plan, I will study lithium iron phosphate battery characteristics and battery management design. David will work with brushless DC motors and will focus on learning their characteristics. Bardia will be tasked with selecting a microcontroller and implementing that into the design. I want to point out that although specific tasks have been assigned to individual team members, everyone will be required to contribute and help each other. And that is the end of our presentation. Thank you. I hope you have enjoyed it.